Essential team. Welcome you all to the Talks and Lectures series. For our third talk, I am glad to introduce Mr. Swayajith sir, who is a pioneer in material characterization techniques. In fact, started his career as an electronics engineer and then moved into the biomedical field, finally doing great advances in the field of material characterization. He has a patent on discovery of a polymer, if I have said so correctly, and he's also a peer reviewer for one of the major journals of material characterization. So without further ado, I would like to invite Mr. Sahadevan for the lecture.
Thank you, Moon, for this fabulous introduction. The crowd here is we are expecting more students. So should I start the presentation or?
So you can start.
Okay. Hope you're all having some background on engineering, science. Okay. Before starting, I just want to ask you about some safety. Because any discussion we start with something related to safety. Okay. So, what is the percentage of oxygen in this? Right answer. Okay, how much it can go low to survive? No, that is feet, percentage level. 10%. Okay, random number. Okay. Okay, see, why I am just starting with the safety conduct in this other culture. Any meeting should start with the safety. So I just want to share that if the oxygen level goes down, okay, up to 70%, okay, there is not much of effect on it. But if it goes further down, okay, your brain do not get sufficient oxygen, and you cannot stand straight. So you sit, and further, if you continue keeping your head above, it would be a serious consequence that when you get a stroke. So, in case of an oxygen deficiency, it can cause due to the height which of the current road, okay, 6,000 feet and above, or due to some gas leakage, excess gases coming in the confined area. Then first you have to give enough oxygen because the blood supply has to break with enough oxygen. You have to lie down. Okay, so this is to just start with the safety. And there are some other policies which we have in Reliance that whenever I am giving some presentation, I have to give an overview of Reliance. And in this Reliance overview, which contains one disclaimer, that means any information which is shared in this forum will be only for knowledge sharing. Okay, and nobody can quote that. Okay, Reliance has made this statement. Okay, it is made by Swayajith Sahadevan. So, and I'm supposed to give a brief introduction about Reliance. That it started in 1966. Established textile mill in Naroda, and in 77 it went public, and the shares were purchased 7 times. Businesses like refinery again, then KGV6, that is Krishna Godavari, Irvine 6 gas production. Exploration started. Then we started, other business, PTA plant for the gas. Then J3 in progress, which is 2017. Looking at the business numbers, which is it's a $51 million company. That is 3.3 lakhs crores, and then annual profit net profit of 20 million. That is 28,000 crores. And the businesses which are training in marketing, which we buy crude and then we refine it and sell it to domestic market as well as export. Then we have a petrochemical, because when the naphtha comes, it is cracked and we make this polypropylene, polyethylene, polyester. And then we have a digital service, that is Geo. Everyone knows, recently, maybe 1.5 years back, it is launched. Then exploration production is probably about Krishna Godavari Basin. We have exploration. The media entertainment network 18 is the channel which is owned by Reliance. And we have a corporate social service, CSR, which we spent 74 crore last 2 years, and it is mainly used for rural transformation, healthcare, education, and sports. We have a sports not audible. Since I thought
actually it's live casted, so for that purpose.
Sufficient.
Yes.
Okay. Okay. So now, in the beginning, I was told this is going to be a life experience of people from external faculties are coming to share their life experience. And I thought what I had to talk about, because I started as a electronics engineer. I completed my engineering in electronics and communication from Many College of Engineering. At that time, there were only 7 engineering colleges in Kerala. There were only 7. And from there, completing my engineering, I joined as a biomedical engineering trainee at Swayajith Institute of Medical Science in Trivandrum. After completing my internship, I moved to Kasima Hospital, Calicut as a biomedical engineer. Then from there, I moved to Mumbai, working with some of the instrumentation and the biomedical instrument engineering companies. Service engineer, summer support engineer, and then I moved to PA Instruments in Bangalore, 99. There I was working as a product support engineer, where I used to go and do experiments with the thermal analysis. And then GE started their R&D center in Bangalore, and I supplied a few instruments. Almost all thermal rheology instruments were supplied by GE. There were not many specialists in that area at that time, so they asked me to join Reliance. GE. Then I started working as a scientist. Then I was primarily supporting the characterization of materials of mostly polymers and some metals. But primarily that division was known as GE Plastics. Okay, our division was GE Plastics, and in 2007 it was sold to SABIC Polymers. And by that time, there was Reliance started a R&D center. I happened to meet one of my ex-directors from GE in a conference, and he just shared with me that they are going to start an R&D center in Mumbai. So then I had an experience of installation of instruments and setting up laboratories. So I moved over there and we set up a 1,000 crore spending R&D facility, which is right side the picture. Here, the R&D center of Reliance, which houses nearly 500 crore worth instruments with the high-end transmission, uh, 20 crores. And the analytical instruments itself is more than 100 crores. And maybe about my stories from College of Engineering, because why I am bringing this, because whenever I was studying, I had a passion towards converting my knowledge into applications. So here, electronic circuit, which is designed by me, the story behind this is there was a construction worker who was visiting my home in the evening, got a slip and fall in front of my home. So why it happened? There was no light. So it's a root cause analysis. In the terminology which we are using in management is root cause analysis. Otherwise, I just asked why it happened. So then there was no light. There was a slippery patch which was leading to my home, where he could not see the algae which were there. So he slipped and fell. Then I thought, why, how I can do something to automatically switch on the lights. But there is a condition. I don't know how many of you have studied electronics and logic circuits. Okay. Can you identify that? Which? Which?
I think so.
Yes, right. It's an exclusive OR gate. That exclusive OR gate has a typical characteristic. That is when the complementary input comes, 1, 0 comes, there is an output. So I connected my requirement that when there is a light outside, there is no need of a sit-out light. When there is a, when all the people go to sleep, there is no need of light. Okay, this is my logic. Okay, there are some plain logic is there. Whenever there is a darkness, the light starts. Okay, the people who are switching on their light from dawn to the next morning. Okay, then you can use a simple LDR. Okay, but here the condition is that whenever at the night, if people are around at home, the light should be on. So if people are at home, naturally the inside light will be on. So there is a on condition. The light condition I consider as 1. So daytime, outside 1, inside also 1. That is light there, light here. So 1, 1, output 0. There is no light, no sit-out light. When it is night and people are inside, outside it is dark, inside it is light. So we have got a 1, 0 input. So the output goes high. This is how I developed a circuit with drivers and everything. This is a basic third semester subjects. Okay, with which I started working. And then I did my seminar on biotelemetry, which is implanting some sort of sensors inside an animal and sending it to study the characteristics of the animal. Wherever it moves, all these things were monitored through sensors. Okay. And that I was fascinated with biomedical and other things, so I thought I wrote something on biotelemetry. Okay, then I started my career as a biomedical engineer. So there is a lot of instruments in medical field. Yes, MRI, CT scanner, ventilator, heart machine, test, X-ray machine. This is just for your information or telling what I was doing. I was supporting all these instruments by whenever it's down, okay, I go repair it. And I learned what it does, okay, what an ECG machine does, what is an EEG machine does, what is a heart rate machine. I was just learning all those things, and after that I got bored. So I just left this field. So let us move to the subject which I'm going to talk today. So the materials. So if you look around, you cannot find anything other than materials. Okay. So it's a fascinating world, and it comes from nature, then animals, plants, and man-made materials. So when we are talking about materials, I'm going to explain more on man-made material and then more into plastics. So type of materials for common man's understanding. That can be metals, plastics, ceramics, fabrics, rubber, glass, which is covers almost everything which you see here and there. Okay, now plastic materials. How many of you have studied plastics, polymers? Okay. So can you relate something with what you studied from this chart? Okay. So what did you study in plastics, plastic engineering?
Not exactly plastic engineering, but like types of polymer, man-made, human-made, how it's linked, cross-linked, thermosetting, thermoplastic,
thermoplastic, thermosets. Okay. So you can answer, you can ask questions also. Because it's a small crowd, so that I can answer. Because if it is a big crowd, the time cannot be managed. Okay, so polymers are, totally classified as it's a soft material, soft polymers and hard polymers, which I will. Plastics. When it comes to plastics, thermoplastics, thermosetting plastics, alloys or blends. Okay, there are many other classification people make, but I just for the simplicity, I have made only categories. And here, this thermoplastics. What is thermoplastic?
like it can be molded into different.
Yes, it can be remolded. That means once it is heated, it becomes melt. Okay, when it cool down, it again becomes solid. Again you heat, you get another product. Okay, it is molten. So it can be recycled. But in case of thermosetting plastics, once it is heated or you allowed enough time, it's a time temperature effect is there. Okay, it become set, and then you cannot use it as the same as it was. Then again, when it comes to thermoplastics, it is divided into commodity thermoplastics and engineering thermoplastics. What is commodity thermoplastics? Any answers? 80% of the materials which you find as plastics are commodity thermoplastics. You go to the supermarket, you find mugs, buckets.
High density, low density.
No,
More like
it is
PVC.
different. It is
PVC.
high. Yeah, you find PVC, PE, PP, polypropylene, polyethylene, polymineral product. All these things are commodity thermoplastic. The reason why it is called commodity, it is in engineering terms, we can say that after 2 years nobody care about it. That's why it's commodity. The commodity, if you go to buy, you use it. But in case of engineering thermoplastic, that is not the case. The engineering thermoplastics are used for specific areas like automobile. You cannot change your vehicle, okay? But every 1 year, 2 years, okay, or few months. You only have to use the automobile for many years, 5 years, 10 years, 20 years. Appliances, okay, you talk about your simple electric iron to washing machine or TVs or anything, anywhere you will find plastic. This electronics, computers, laptops. Then aviation is your area. Spacecraft, aircraft, and you can do more and more. Okay, now again going back to little basics on plastic. It can be a crystalline or amorphous. What is the difference between crystalline and amorphous?
Pattern is crystalline.
Huh?
Pattern.
Yeah, the crystalline, there is a pattern.
Repetition.
Yeah, repetition. It is in an ordered manner. The molecules are arranged in an ordered manner. So it's crystalline. And there is no 100% crystalline plastics or polymers. It's the reason that the polymerization process is like that. Okay, you cannot get that much time to get it ordered. But highly crystalline polymers are there. Okay, which will have a very when you look at the melting point, you will find that it is it has a sharp melting point. Otherwise, polymer will have a broad melting point. And again, amorphous. Amorphous, there is no water. But is there a melting point for amorphous polymers?
Range.
Range of melting point? No. Okay, the amorphous polymers have a temperature of processing which is known as glass transition temperature. Okay, that it moves from a solid state to a semi solid state. Okay, it becomes soft, and you apply pressure and temperature at higher temperature and pressure, you can mold it into any part. But in crystalline metal, there is a sharp melting point, after which it is amorphous. After the melting point, it becomes amorphous, and when it's cooled back, okay, it reorders and becomes again a crystalline polymer. Now, quickly going into the product development. We have made polymers. Okay, we have seen polymers. How the polymers are made? That is chemicals. Okay, you have chemicals, catalyst, conditions. All those things goes into a reactor, and from reactor you get polymer powder. Then this powder goes into an extrusion machine, and the extrudate is pelletized to get pellets, and this pellets goes into a molding machine, and finally you get a product. Okay, this is the product side. I will take each of these product sides. The reactants go into the reactor, and the product comes out. Okay, there we are giving temperature, pressure, catalyst, conditions, all those things. But is it that simple? A reactor? Okay. This is our polymer reactor. Okay. Unless and until you work in an industry, you cannot imagine those things. Okay. Otherwise, in a test tube, you can make many things, but that will not work for the market. Okay. Okay. Now we have got this polymer powder from the reactor. Then this polymer goes into an extrusion machine, the extruder. It goes here with a lot of feedings are there. The polymer as such cannot be used for any product making. Okay, then it goes for some additives, which gives the thermal stability, UV stability, then antioxidants and are used for anti-aging. And all this goes inside, and there is a screw. Okay, the polymer powder goes here, then the screw runs and it melts and it comes out. Okay, so if you don't pelletize it, it just accumulates like noodles. Okay, continuous noodles comes out of this. Okay, if you I don't know, have you seen an extrusion machine in somewhere? Okay, so have you seen the material coming out? Yeah, good. So then a pelletizer which pelletizes it and got polymer granules. Now we go to the molding. So this is our molding machine. This is a small, symbolic representation of molding machine. The large machines are too huge. Okay. Now again, this polymer material goes to the hopper. Then there is a screw which comes and give ultimate shear. So that there is one topic which I am not taking here, but I am just talking about is a shear. Okay. When this material, the rheology part I am not covering today. See, when this is stamped in this injection molding machine, the material becomes very thin. That means its viscosity comes down, and when the viscosity comes down, it just flows like water. Okay, so otherwise, unless and until we give such a high shear, you cannot get products, and there are so much of engineering and science going behind the processing, and I cannot cover it in unless and until I get 2 days, I cannot cover that processing techniques. Okay, then it can be a molded part. Okay, depending on the complexity, we get the parts as assembly as a full product or maybe a part. Okay. Okay, let us go to the next materials in aerospace. Okay. See, this is in an aircraft. Okay, I am just referring to aircraft because I have seen only aircraft. So I don't know whether you have seen spacecraft because you have the opportunity to see some of these launch vehicles and other things which I never got an opportunity. Okay. See, when we are selecting these materials, because now we are coming to the material selection, we look at the properties which are required for each area. Okay, this is only for example for just giving you an idea about the properties which are manifesting to get into this aircraft, which is it is a control system. You're looking at it should have the materials which are used in here. It should have enough heat resistance. Okay, the heat generated should not pass to other part of this aircraft, and then it should have electrostatic dissipation. Okay, whatever electrostatic force, the electrostatic generated should be dissipated, and it should be of lightweight because always the aircraft industry was looking for reducing the weight of material, and should be highly insulated. And if you look at the propulsion part, okay, there is a static resistance. Static is the repeated mechanical loading, vibrations. This gives it's a long-term mechanical testing. The wear resistance, whenever there is a moving part, whether it is a gear or it is a peristaltic pump or gears, ball bearings, these are always keep on moving. And if you look at metal, it is heavy. And when you use plastics, it is light, but there is a where where tear and wear is very high in those plastics. Then fuel resistance. That means any plastic when you take, okay, that inherently not resistant to chemicals, not even for water for that matter, to certain plastics. Okay, if some plastic material come in contact with water, it's going to fail. Then BAC fluid resistance. Like, what are the environment at which this plastic material is going to work on? That is the BAC fluid. I think it is glycol. Okay, when these plastic materials are coming in contact with this parts, it's going to fail. So we have to take engineering measures or design the plastic, select the plastic such a way that which is chemically resistant. Or structures, thermal insulation. Okay, see the temperature which is generated in the engine, it is very high. In the order of, it can go from 200, 300, 400, 500, 600, any temperature, depending on the kind of aircraft it is. If you see the fighter planes in the back, you can see, flames coming out. Okay, it is red hot. Okay, then low friction. The low friction, the friction, material to material friction is there, air to material friction is there, the surface finish. All this matters in selecting those materials. Chemical resistance. Hydraulic hydraulic fluid which is used in air. And then interiors, the plates are messy, noise reduction, lightweight. See, how many of you have observed the noise from a mix at mixing? So, have you heard about some mixing that quiet, silent? How it is achieved? How do they achieve silent? It is all. There is a motor, there is a body. That's it. But how they achieve this noise reduction?
Damping of the vibrations.
Yes. How?
material that can not transmit the vibration to the other.
Okay. Okay, see, it is in engineering, in plastic engineering, what they do, they add materials which absorbs that energy. Okay. See, if you add rubber, more rubber to this material, to a polypropylene or polyethylene, what happens? That material becomes soft and it will not make flux. But at the same time, what happens? The strength of that material goes down. So you optimize in such a way that select the right material and process the material with additives which will absorb that energy. This noise reaction, flame retardancy. You know what happens when something catches fire? What all things happen when there is a fire incident? How fire is occurring? You get basic fire training in your courses. Basic fire training. You have heard about a lot of accidents, fire incidents which are happening due to short circuit, due to gas leak, due to say, a fuel leakage. See, for fire to occur, there are three things which should be present. First, temperature. Second, fuel. Third, oxygen. Okay. The beginning I talked about oxygen. Okay. The oxygen for our life, similar to that, the fire also oxygen is like that. See, when sufficient material is there, and if sufficient temperature is there, oxygen is around, and a small flame can create a big fire. Okay. So, when we are selecting materials for aircraft interior, it should have a very low flame rating, because flame ratings are like how much time it takes to catch fire, and when it catches fire, okay, what are the consequences? Most of the time, the people die in a fire incident is not because of burns, but because of inhaling toxic gases or inhaling particles, smoke. So when the material is selected for interior, it should have a flame retardancy, because even if you light a lighter and keep it near to the plastic, it will not catch fire. Okay. Now it's right, like the lightweight and design friendly. If you want strength, okay, you can go for a high molecular weight material, but whether it can be processed in the way which you want, because if you want to mold large articles, you have to have a viscosity which is very low. Okay, then only you can make big articles like blow molding and different molding processes are there. Cannot cover it in this session. Okay, so engineering design data. See, when you are looking at a material data, there are nearly 70 different data which is measured in the life of a plastic for an application. Okay, starting from reactor to the end product, you have more than 70 parameters which are measured. Okay, the first, normally they go for MFI, that is melt flow index, how the material flows. Here, I am talking about engineering design data. In engineering design data, there are a handful, like maybe 15, 16 parameters with which you can design engineering part. First is tensile, fractional, then compressive. These are all mechanical properties. And then impact, again another mechanical, how much energy is required to break that particular material. then thermal conductivity, coefficient of thermal expansion. These are the two techniques which I am going to explain in the next coming slides. Let us move to a composite material. Okay, what are the properties which you look for composite material? See, here if I am taking the body paint of an aircraft, which is modeled here, you can find many parameters which is given here. CDE, coefficient of thermal expansion, heat capacity, density, thermal conductivity, ratio. All these are critical for designing that material. What happens if the CDE of one layer is very high? It is not going to stick. The moment the temperature variation happens, like an aircraft exterior is going to experience a temperature range between -42 all the way up to 50-60 degrees centigrade because it is traveling across the globe. So, if a material which is having a coefficient of thermal expansion very high, it will not fit into this. So, we have to measure the coefficient of thermal expansion. Then, heat capacity. The heat capacity is the heat energy required for raising that temperature. Okay, how it is going to absorb that energy. Then density is for lightweight application. Then thermal conductivity. Thermal conductivity of material, which depending on the structure, you have to design the material. In certain layers, you need to have high thermal conductivity, and in certain layers, you have less thermal. And then dense modulus, that is the P strength and then Poisson's ratio when it is stretched, how it is going to change the modulus. Okay, this is an example of various parameters, various properties which we look at, and then some of the materials which are used in aircraft. Acrylic. Okay, why acrylic is selected? The acrylic is selected because it's transparent. It transmits 92% of white light. Okay, and it has a very good impact strength. It is used in exterior. Okay, if a small bird comes and hit, okay, it should, because the momentum which carries when an aircraft lands, it's too huge. The velocity and the mass, okay, that creates the momentum, and with that impact, it should withstand that energy. Okay, and it should have a very good dimensional stability and low moldability. See, whenever this material is selected, the design, once it is designed and extruded or molded out, okay, it should maintain its size, dimension, shape as per design. Most of the plastic material have this drawback of mold shrinkage. Okay, you mold a material with a thickness of 10 millimeter, and when it is, if the mold is designed in such a way that it is, 10 millimeter, by the time you get the product, it may be 8 or 9 millimeter. Okay, this is the dimensional stability and weatherability and resistance to sunlight, because this is used in exterior, and plastics are inherently not resistant to the UV, ultraviolet. Okay, when UV comes, a transparent material will turn to yellow. If you look at some of the cars headlamps, okay, when they go and replace, normally in India, where you will find one of these headlamps are getting broken, and if you go to a local shop, you will get this headlamp. By buying, it is clear, transparent. But after 3 months, 6 months, you will find that it is, one lamp is the one which is bought for low cost is turned into yellow. Why? Because of its low UV resistance. Okay, and it oxidizes and it turns into yellow. So in aircraft, in aircraft or in the engineering application, you cannot afford such, such low quality materials. Then polyamide is problem. This also labeled as no smoke comes out while burning. Okay, the smoke which is coming out of a material, out of plastic, is very critical for safety. Then it is stable up to 260. Most of the materials which are used in the aircraft industry are high temperature, materials. Because normally, if you look at polypropylene or polyethylene or polycarbonate, most of the material service temperature is below 150, 100 degrees, 110, 150, that range. Okay. Then ETFE. ETFE is also known as Teflon. Teflon is very flexible material at low temperature. What happens when a plastic material is taken to very low temperature? What happens?
Brittle.
It becomes brittle. You just crush it. It become crushed into pieces, just like puppet. And this material, even at minus 100 degrees centigrade, it is flexible. It is always show the ductility, not the, and it is having a very low coefficient of friction because this is mostly used in the cable. The cable, bundles of cable are running through this aircraft, inside aircraft. Where if you want to, when you are pulling one wire, okay, adjacent wire, if it is having a high coefficient of friction, then it can tear the other cable. So it should be smoothly coming out from the. Then, of course, it is stable at high temperature. Yes, and very isn't really flammable. Because most of the material, the flammability. There is a company which is known as UL, Underwriters Laboratory. They certify this material for its flammability. Okay, so if you take any material here, okay, any plastic, even if I look at here somewhere, there it will be UL certified. Because you cannot sell this plastic for reputed industries without UL certification. The UL certification says this particular material is, having the flammability rating so and so. Then PEEK, which is it is almost a replacement for metal, and many instruments are using PEEK as the screws. We can make screws, nuts, bolts, pumps with PEEK. The reason it has an excellent chemical resistance properties. When almost everything, even if you put it in many acids, nothing will happen. That is the nature of PEEK. And its melting point is somewhere close to 400 degrees. And it has a very good shear resistance. It can be used as screws, because screw, when we are using, you are applying a force in the twisting manner, torsional force. Because the bulk property of this PEEK is excellent. And as usual, very low smoke and no toxic gas emission. Okay, these are the materials, because most of them are trademarks of many companies. I personally work with this metal. In polycarbonates, we have Lexan polycarbonate, Cadence and DuPont Vestel. All these are, this company's, trademark products. Okay, now coming to the last session. Was 1 hour. Okay, I curtailed it. Otherwise, I had a lot of stuff to talk. Okay, I talked about some 70 properties which are set for this. If you look at broadly, it can be classified into mechanical properties, and in mechanical properties itself, there is a short-term property and a long-term property. What is short-term? It is instant. You can conduct that experiment in a very short duration, or if the material is going to undergo condition which is short in nature. Okay, and there are long-term properties like weathering. If a material is exposed to the outside condition, the measurement is long-term. The property which is to be measured is long-term because we do not know how many years this material is going to be exposed to the sunlight. Okay, that is weathering. This is a long-term property. Then here, three stress relaxation fatigue. Three properties like if it is under stress, okay, if it is loaded and kept it for some time. Example, the bushes which are, I don't think here any chairs will have bushes. Okay, these bushes, every time these bushes are getting loaded, its own weight plus the human weight, whomsoever is sitting there. So we have to look at the creep properties of that material. How we constantly load the sample and see how it elongates, how the material elongates or compress or twist. Okay, the continuous force which is applied. It is long term. And fatigue property, cyclic vibrations. Okay, an engine, as long as it runs, this material is going to undergo the fatigue. These are long term. Then flexural properties, compressive properties. See where it is being applied, where the material is being applied. See, look at some beam which are kept between two studs, and if you are applying some force, it is going to undergo a flexural loading. I'll show you a couple of slides, a couple of pictures on different loading conditions. And then these processing parameters, water shrinkage, viscosity, solution viscosity, viscosity versus shear weight curves, flow rate. These are all simple, MFI, MFR. These are all simple measurements. But looking at this creep measurement or fatigue measurement, which is very complex. And the thermal properties, DTUL, that is deflection temperature load. You load a material and see, over a period of time how it is going to deflect. So the coefficient of linear thermal expansion, I mark it different color. I am going to explain those properties here in detail in the coming slides. Specific heat, relative thermal, relative temperature index, RTA. This is another property which is measured by UL. What it does, they keep the material in oven at elevated temperatures and keep on taking it back on a period. You load hundreds of thousands of samples in an oven, take it out on a weekly basis, and then you measure the properties, pliability, tensile properties, and mechanical properties, and see how the material is going to behave over a period of time. It's a long-term test. So what happened, because the material which is undergoing such conditions, okay, we are going to use certain materials at high temperature for a long time. Today, immediately after the material coming out of your molding machine, have a mechanical property, say like its tensile strength is say 10 megapascal. But if it is heated for some time, the internal molecular structure is going to get disturbed, and it is it loses its property. It is mechanical integrity is lost. And see look at some of this plastic buckets. Okay, you keep it in sunlight for some time, it becomes red bucket turns into white. Okay, the dye is anyway gone away. And if you keep a white bucket, it becomes brittle after some time. Okay, so then electrical properties, because a lot of materials which are coming in contact with electricity, then dielectric constants, polyol resistivity, surface resistivity, all these parameters. Because see, the cable which is carrying the current should not get shorted with the adjacent cable because of the electrical conductivity of plastic material which is used in between. Okay, see, this this is too huge, and if these two slides itself could be, a semester full of topic. Okay, you can have a full semester for covering mechanical and these properties of materials, studying how it is measured and where it is applied. Okay, this mechanical properties of polymers. Have you seen this? Okay. Have you seen this machine? What is it known as? Huh? UTM. Why it is called UTM? Yes. It is universal, universal mechanical testing machine. UTM. Because it can be used for tensile properties measurement, flexural property measurement, and compressive property. Okay, so here there is a sample. Have you worked on this machine? Have you mounted sample? Okay, so you loaded the sample and measured the mechanical property. Then I for the interest of those who didn't. In this, there is a load cell which measures the stress, and there is an extensometer which measures the strain. The stress strain curve gives you all the properties, tensile properties. Okay, so here there's a curve which talks about proportional limit. This is the limit by which the stress strain is going to be linear, and then it is having an elastic limit. That elastic limit is the limit till that point. Okay, the material, once you release your applied stress, when you reduce it to zero, this strain comes back to zero. Okay, the only difference between proportional limit and elastic limit is up to proportional limit it is linear, and here it is non-linear. This region is non-linear, and then this yield point, that is the point where even if you remove the stress, the material will not come back, and then it goes for ultimate strength, and at ultimate strength, it reaches the maximum strain, and then in this region the strain happens because if you look at the material. Have you observed while the test is going on? See, initially you cannot see any difference. After some time, it goes stretch, and the thin material comes, and finally there will be one area, one small portion, which become narrow. Okay, to break. So this region is up to here. We can say this is ultimate strength, and beyond that we don't. Here, what happens? The thickness of that sample goes much bigger and become separate. Those two pieces getting separate. And again, what we get from this pressure? Okay, whether the material is brittle or ductile. The material which is elastic, and then it directly go to a brittle failure. If you, the example is glass. If you take a glass piece and try to measure, you will get this type of curve. Okay, many polymers also there. I will show you one of them. And then this area under this shows the strength of that material. Okay, and to understand the yield point, okay, if you take the paste and apply some stress, okay, it doesn't come out. And if you apply more stress, it's come out. When the yield point crosses, it starts flowing out. Okay, the press which you are giving, okay, that is the stress. And after that, even if you release it, it will not go back. Okay, if you just to understand the modulus and strength, is see, look at the modulus of pencil and a chalk. This is made of wood, and this is our chalk powder. Okay. If you look at the slope, it is the same. So the modulus is same, but the strength is the area below the curve. So pencil have a more strength. So this property is used in not only in mechanical, civil, everywhere. Okay, strength of materials are calculated whether it is compressive or it is flexural or it is tensile is measured from. Okay, and different type of curves, material, how it behaves in elongation, how it elongates, and this is a two-dimensional material, elastomer. Keep on going because all the curves cannot be placed in one scale, so there is a breakage. Okay. In other ways, flexural strength, tensile strength, compressive strength is represented like this. Okay. So where you are going to use the material? Okay. If the material is going to be used between two studs as a B, you have to look at the raw strength. Okay. Just simple, the material. Suppose you put the PCBs. I don't know how many people are electronic enthusiasts in this group. Okay. So you do some assemblies. When you do some assemblies, okay, you have to understand the kind of materials and what is the kind of force which you are applying on it. See, in the when you are fixing the screws of certain boards or materials, how much you can tight? There should be a limit. Okay, if you tight more, depending on its compressive strength of the material and the structure of the whole assembly, there could be a failure. Okay, that is where you should understand these properties right spirit. Okay, so this the same modulus, but when the load goes up, it goes down. That is, modulus is the resistance for deformation. But if the low modulus material, it also the modulus is explained here in two different occasions. Okay, low modulus material, same modulus material, when the load is more, it again cannot withstand. Okay, now thermal conductivity. See, thermal conductivity is a measure which is very critical for aircraft application, as I told you earlier. In the control section or the part which are connected to the near to the engine, there's a lot of heat generated, and how to prevent the heat coming into the other areas. You have to have material with appropriate thermal conductivity. In certain areas, you need to have thermally conductive material to dissipate the heat from that. Okay, you have a cooling fan, and if your if your material is not dissipating heat to that side, okay, you are going to you are getting into a failure mode. And the simple example is electric iron. Okay, if you have a material with a high thermal conductivity which is used, what happens? Initially, nothing will happen. Okay, but after some time you cannot use it because the heat in the plate is getting transferred to this plastic material. Okay, so you have to have a material with very low thermal conductivity for designing this material. This portion of that applies. Okay. And in practically this thermal conductivity in process engineering, because in any other part, okay, we can just measure the thermal conductivity with the various techniques. But here I am just talking about a technique by which we measure the thermal conductivity. There is a thermal conductivity probe which is having a heat flux sensor, and it goes into a molten material and it is sealed, and we apply pressure and increase the temperature. Okay. At various temperature and pressure, we get the thermal conductivity of that. This is an instrument made by what company who makes this instrument, and this data is used for mold flow analysis. This mold flow analysis. Have you studied mold flow analysis? Because you input parameters like heat capacity, thermal conductivity, motion gauge, thermal conductivity by line source method, then tensile, tensile properties, CTE, all this engineering design data has gone into mold flow to get how your molded part is going to come out. To get this detail, you have to measure thermal conductivity. Okay, another one is coefficient of thermal expansion. Here is an instrument which is known as TMA, thermomechanical analyzer. As a function of temperature, the dimensional changes are monitored in this instrument. And the fundamental principle at the room temperature bar, when it is heated, it is going to elongate by delta L, and coefficient of linear thermal expansion is measured entirely by L, the difference in temperature, and it is meter per degree centigrade or micrometer per meter per degree centigrade the unit comes. Okay, so that is how theory goes. And let us look at practical. See, this is a bullock cart. I don't know now you are able to see it. Okay, in some villages you still you will find. How do they make the wheel? See, they cannot put called now there are all different type of hardness drills are available. You can drill holes and put nails and fixtures. But olden days it was not there. So what they used to do, the wood is cut. Carpenters were good at that time, and they go to they heat this metal thing, okay, and it expands. Then they place this wooden ring inside and let it cool down. That's it. And it will be there forever. As long as the metal is there, the fixture is there, because that is the power of coefficient of thermal expansion. And you would have seen this in railway track, there is a gap. The gap is provided to accommodate the thermal expansion of this rail during the summer. When it is winter, the gap will be more. And if you don't have the gap, okay, if a technician like it fully across, and this is another major area where the CTE is very, very critical. The reason, you cannot work without a plastic and a metal combination anywhere else. Okay, in PCB you have to have metal, because no polymer conducts as good as metal, and you cannot use metal because there is no metal which is non-conductive as plastic. So to make your circuit, you have to have the combination of metal and plastic. Okay. This plastic have a high coefficient of thermal expansion. They expand very fast, and the expansion ratio goes very high when it processes at glass transition temperature. And whenever and electronic components, if you look at your laptop, there is a fan inside. Why? To cool the CPU. So the CPU is going at temperatures which are as high as 110, 130 degrees. Some of if you look at some windows of the diagnostic tool, if you open, you'll find what is the temperature of CPU, and the math core processor, what is there. Okay. Every component temperature it shows, and if that expands at a certain CTE, and the plastic expands, plastic also going to experience the same temperature, and if there is a mismatch of CTE, it's going to fail immediately, because if, you would have seen the PCBs how it is made. It is micro cabling and multi layers which are going. So you cannot afford any mismatch in the PCB design. Okay, this is how it is measured. Because there is a sample, there is a quartz stage and quartz probe. Why quartz? That is the least, dimensionally the most stable material. Okay, so if this do not contribute much of expansion, but only the sample contributes the expansion measure. And the principle by which it works here, there is a sample, there is a node which is connected, okay, and here is an inductive transducer. This is LVDT. What is LVDT? Linear variable differential transducer or transformer. Okay, so when that moves up and down, it measures the change in dimension. And this is, if you look at the change in dimensions are in micrometers, that is 10 raised to -6. And here the sample is given in millimeters. And it's almost 1,000 times it has to measure. So that is why this transducer is used. And normally the CTE is reported from -14 to +14 in a data sheet. The reason that is the region in which most of this aircraft operates. Okay, again, it moves from India to Africa, Europe to America to ports. So it is going to experience that temperature. So always exterior material use this -14 to +14 as a data point. Otherwise, for specific application, we have to measure it at higher temperature. Like if you are going to use PEEK and PDFE, you have to measure at very high temperature, the CTE. And the comparison of material expansion, plastics are always high and glass is the lowest. And that is why it is used in the instrument construction. Okay, this is my favorite subject. How many of you heard about dynamic mechanical analysis? Okay. Okay, how did you come to know about DMS? Yeah. Okay. Have you seen this instrument? Which one? Okay. Different makes are there. Perkinel, TA instruments, Nectar, so many different instruments. Anyway, it's a versatile instrument, and this is the one instrument which gives the mechanical properties for a product as well as the molecule. See, mostly material characterization is used for structure property correlation. The structure property correlation is the molecular structure as well as product structure. Okay, so this instrument which talks about the transition temperatures. Okay, when we are talking about transition temperatures, the transition temperature is contributed by the molecule. And polymers having a backbone, then branches. So any change in branches contribute to a transition that is known as beta transition. And the alpha transition is the transition where which the processing parameter is determined. The effect of crystallinity on glass transition. See, by doing dynamic mechanical analysis, we can differentiate different crystallinity of material as a function of its glass transition. Because I have to go much deeper to the chemistry side on semi-crystalline polymers to make you understand in a deeper way. But what I can say, the versatility of the instrument is to get the structure correlation with the chemistry and effect of proximity, of build-up on modulus, polymer blend visibility. See, I talked about polymer blends and alloys in the beginning. So when you are mixing two material, okay, whether it is really mixed or it is standing as two separate material, okay, that can be measured by, because when two materials are mixed, suppose you have a material with a glass transition temperature of 100 degree and 150 degree. If it is 100% visible, you should get a glass transition of the blend in between 100 and 150. But normally, which instrument is used to measure glass transition temperature? Tipping point. Okay, not TGA. There are instruments which is coming as DSC and TGA together. Okay, DSC, TGA together there is an instrument. But otherwise, normally we use DSC, differential scanning calorimetry. Okay, that is not as sensitive as DMA. So there you may not find the real transitions. But in DMA, which can pick up even minute transitions which are happening due to the branches of the molecule. Okay, that is where the visibility of a polymer blend can be clearly seen by using DMA analysis. Then, at the same, the mechanical properties, whatever we talked in the earlier, which are all related to the unidirectional. But here, if you look at this, there is a force stress is applied both directions. Okay, sinusoidal stress is applied, and corresponding strain is monitored. So, as a function of temperature, frequency, and strain rate, you can measure the mechanical properties, and which gives you the next curve. And go to the next curve, then come back. See, here you get two modulus. Okay, one is the storage modulus, and the other is the loss modulus. This is the loss modulus. This is the text. Okay, so when we are applying a sinusoidal stress and strain, we get the viscoelastic properties of that material. Okay, there's a plastic is a material which is having both viscous component or viscous nature and the elastic nature. 100% elastic is not. It is neither 100% elastic nor 100% viscous. It is viscoelastic. So this modulus, the viscous modulus talks about the energy dissipation into the material. That is where the noise reduction is. Suppose you want to do a noise reduction in a material, you do a DMA and find out, how much energy is being, absorbed during the entire scan. So there you get the information on how to tune your material to reduce the. Here it shows the modulus of materials. This diamond which is having 1000 GPa, and plastics starting from 10 GPa. And if you want to get somewhere around, more than say 10 GPa, what you do? You need to use plastic, but you need a strength which is more than 10 GPa. You can do reinforced polish. Okay? You put glass fibers, carbon nanotubes, carbon fibers into the material and extrude it and get a material which can go to very high modulus. Okay? And one more point on this slide, as I talked earlier, the structure property correlation. If you look at the minus 80, minus 100, okay, minus 80 degrees, there's a transition. Okay, this is the glass transition temperature of this material. I think this is polycarbonate. Yeah, it's polycarbonate. It's alpha transition. Alpha transition is around 150 degrees, and which is a huge transition. It's a multi-order transition. And here it is having a beta transition. So if the material is being used for application which is below 80 degrees, the modulus is different. Okay, elastic modulus is different. This elastic modulus talks about the surface temperature of the material. Okay. And now I go back to the previous slide and explain that effect of filler. The different fillers, amount, sizes are added, and with the DMA analysis and took the single point data. So here it is EPA. Okay. gastric modulus of elasticity or gastric modulus is given. And see, this particle fiber was given, and different loading happened. But what happened? The modulus is not really increased. But when it is going to long fiber, and when the percentage loading has gone up, the modulus has gone from 5 megapascal to 23 megapascal. If you look at the next slide, it is 25 megapascal is somewhere here. Graphite. Graphite or magnesium. So if you want to replace magnesium with plastics, you have to use this material with the fiber, long fiber. Again, this is the surface temperature. The service temperature is it's starting from room temperature to going all the way to 10 degrees centigrade. We are looking at the modulus of this material over a temperature. And if you want to use this material only up to 150 degrees, okay, depending on the application, this material say this material costs $300 per kg, and if this is available for $100 per kg, you can take 1/3 of this material. If the application is going only up to, if the operation is between 70 to 100 degrees, something like that. See, this is where we apply this material characterization techniques to optimize the economics of the industry. Now, see again, this is a comparison. I think that's all I have with my strange career. That coming back to my last slide, where I was. If you have patience, then I will explain. Otherwise, I will not. See, this is in my Fatima hospital when I was working as a biomedical engineer. The open heart surgery was happening, and that was the first surgery in the private sector. The doctor asked me to be a part of that surgery team. Very rare opportunity. No engineers were allowed in operation theatre, but I got that opportunity. And surgery started. Heart is bypassed. Right. Now the patient is on machine. Okay, if the machine fails, patient is gone. That is the situation. Where immediately, that time there was not much of this UPS power supply was not there. There only backup, generator backup. Generator started, but heartline machine didn't start. Okay, see that time it's a very critical situation, and the perfusionist is the person. The perfusionist is the person who operates this heartline machine, and he was trying to manually keep the pump because this can happen. So they were trained to use. There are 4 pumps are there. He was with another perfusionist. They were moving it like that. And again, how to maintain the speed and rhythm of that heartbeat, because machine everything is set. At that time, since the motor is not working, either it is a the motor is not DC motor. Okay, there could be some capacitor which is charged and it's not giving the sufficient voltage to start the motor or something. What I did, I had the toolkit with me. I just opened the behind and then I removed the back panel. I made a master reset. All charges gone, and I put it back. The machine started working. Okay, this is the one case, and the second case was at 2 o'clock. The ambulance came to the lodge where I was staying and told that there are 4 or 5 ventilators, and all the ventilators are connected to patients, and one ventilator is not working. And ventilator is an instrument which is used to assist the breathing. Okay. Normally, what happened when the ventilator goes down, one nurse, okay, OT nurse, she goes and we put amplification. Okay, she just presses so that the rhythm will be maintained, because much before this also the surgeries were done. But at that time I went and checked the ventilator is not working because there was a fuse which is blown off. At the night, no service support will be coming from vendor. So no shops are opened. So what I can do, I just find out it is a slow blow fuse, and then I opened another 4 instruments which were idle. Not ventilators, that ECG machines were there, EMG machine was there. All this machine opened and I found the matching fuse 1.5 ampere slow blow. I just replaced it and okay, these are the 2 things I do. Having a better reporting of that is that we wanted to improve the clarity of a material which is layered silicate added to polypropylene, and one of my friend and we two work together. I did the entire characterization of that material to identify the crystallization temperature, because crystallinity is something which matters the phase of the material. If it is more crystalline, more opaque, okay, that is the. So we removed the, we made the material to crystallize, not to crystallize that fast, and then we made a much clarified PP. That is what we got. And then publications, the two I showed you in my electronic circuit, when I was a student, then and the rest all related to material characterization is used for in the GE plastics, where I worked on thermal, rheology, mechanical, and those applications. We got a lot of opportunities. Working as a scientist, you get a lot of opportunity to publish papers. And thermal and rheology, at that time, I got my job itself because of the, because of thermal and rheology, because it was a very niche area where many people were not there. Okay? Very few professors were there who was teaching. But by practical experience, working with customers, mainly with the defense organizations, the DRDO, then DAE, LRD, so many institutes were there in Bangalore. I used to go and work for them to identify their issues and provide solutions. And currently, I am working as a risk manager, which is a portfolio of finance management. Whenever you are taking loan or insurance, okay, these are all related to risk management. Okay, and I am working on risk management of R&D operations where IP risks, intellectual property risks. Suppose you are working on some project and finally you infringe somebody's patent, then ultimately you waste your money as well as reputation at the later stage. And there are huge risks associated when you are working with big corporates. Okay, in small companies it hardly matters. When you are working with very big corporates, okay, the company has enough money, anybody can sue. And that is why I shown my first slide disclaimer that okay, whatever information which is passing here, okay, it is from Swayajith, Sahadevan, not from others. And okay, this is the standard. In 2006, actually, the necessity is the mother of invention. That is the kind of thing, because that time we had a audit, and the auditor came and asked me, okay, where is the calibration standard? So I told there is no calibration standard. Without standard, how you can operate this machine? Then I contacted ASTM. They told there is no standard existing. Then I told, can I suggest a standard to you? I wrote to ASTM, telling that okay, this is the method by which we can calibrate this. The loss modulus of certain materials can be used as a standard. That is a reference. Okay, it is not a it is a conformance. It is not a calibration. When I got this recognition, that the next time the auditor didn't have any words. Okay, he had to accept. Okay, in this R&D operations, the competency makes a lot of difference. Okay, when the regulatory body versus scientific community. Okay, the scientific community is the competency is sufficient enough. We can defend any of this regulatory requirements. Okay, that's all from my side. And one thing which I learned from my college, MI College of Engineering, is knowledge is power. That means, okay, you keep on acquiring knowledge, irrespective of the area, which is from my own example. Okay, I never stopped learning. Even now, I am learning. Okay, keep learning. to enhance your knowledge, and that is your goal. And growth is like my company says. As I told, it started as a small, textile mill, and it gone to the India's largest private sector company. Thank you. Trying question: how many of did you gain anything out of session? Because if you have any doubts, okay, you write to me, because I am not that a great orator to explain everything, because the subject itself is little, you know, uh, strange to the students level, because these instruments you may get to know into the beginning of these things, but getting into the details, you need to work in the laboratory. And I learned most of this thing by hands-on experience. Okay, so if you have any doubt, okay, you can just get my email ID from phone and write back. Thank you. So any questions? No, hardly. I asked few questions to you back. Have any questions? Anything? Because I didn't cover the entire topic. I just took 2 or 3 topics like tensile test and CPE and.
So actually, I was intrigued when I read that you had a patent about a polymer. So could you just tell us all a bit about it?
Patent?
Not patenting per se, but the polymer that you processed.
Yeah.
Even the papers that we saw that you published, one of them was on aliphatic polymers, right? So if you could just tell a bit.
Okay, see, most of my publication part coming from the characterization side. Okay, see, I remember in this particular nanomaterials which we are used to enhance this crystallinity, which is the crystallinity, which was pushing. I cannot go into the details of the chemistry because I don't have a background. So we, we process this polypropylene with layered silicate. Okay, and these layered silicates were enhancing the crystallization temperature. That's what my friend did, and I characterized it using DSC. And many other things like applications which are vapor point depression. That is something which never did. Okay, the people know that BBT with the compound, because it's a totally chemistry terminology. And what I did was, I did a BSc experiment under pressure condition, which seal the material in a container with which can withstand up to 1,500 psi. 1,500 psi. So that the material will never get evaporated from that. And at that time, I measured the melting point depression from PBT, which is having a melting point of 225. The melting point was depressed from 225 to 196, which was experimentally nobody was proven. Because the moment you use normal DS is what happens. When the temperature crosses somewhere around 60 or 70 degrees, the solvent which get evaporated, then you are getting nothing but PBT there. Okay. See, these are the the contribution which I made for my publications. Okay, the entire characterization part I was. Okay. Any other question? Mechanical, thermal, rheology.
Like, what about the manufacturing of these polymers in the zero gravity and vacuum? Like, what are the possibilities? Like weak you showed us, it's almost a replacement of a metal.
Okay.
But in future, like we know, we could manufacture things in the outer space or on the other planets. So, what about the manufacturing at zero G?
Sorry, I cannot answer that question. I don't know. See, my level of understanding of that chemistry is not like a polymer scientist. Okay, I am mostly with the material physics. Okay, the subject which you are talking about is a chemistry polymer scientist who would be there.
So we had a small presentation as a talk about that. So one of our artists in our batch.
Oh.
Made this.
Thank you so much. So, thank you so much. I'm really pleased to get somebody get into Facebook or
We just Google.
Google search, okay? Because I am not in this social media. I have LinkedIn, and that is rarely looked into. Facebook, I don't get into. Thank you.
Thanks so much.